Alrighty, welcome guys to this final episode of Intro to Networking, where we are talking about how to do GRE stripping on the packets that are inside this GRE tunnel. In other words, we're just going to remove the GRE tunnel. Now, before we start, I just want to give a shout out to all the free tools that we use during our design work here. Things like WaveDrom for drawing waveforms, the GTK wave that helps us analyze the VCD files. Obviously, myhdl, a great tool for coding in Python, trying to code hardware stuff in Python and then simulating it and converting into VCD files, which GTK wave can then show us the waveforms, thus emulating all of the environment that we normally do to develop hardware, except for zero cost. So that's fantastic about this whole environment, something that you should definitely try if you haven't done so. This is an excellent environment to try out your ideas, even without expensive tools that cost thousands and thousands of dollars, or unstable environments that are kind of not worth the time, tools that are unprofessional and not ready for spending enough time because there's too much errors in them. So, yeah, go ahead and try these and let me know if you have some feedback on these. Now, moving forward, let's look at this final episode. Now, this episode, because there's too much code involved, I'm not going to do hands-on on this. I'm just going to try to explain things, and then if you guys want a code walkthrough, then I can do another episode. So if you really want to see the code, leave me in comments, and I can go over code. Or if you want to see specific things, let me know. But otherwise, it really falls out of what I've already shown. In general, it's more of the same. The critical part is how we do certain things, and that's what I'm going to show in this episode. Now, to do GRE strip, just as an overview of the whole process, what's going to happen is that in the previous episodes, we have seen how we parsed layer 2, layer 3, layer 4, and layer 5, which was GRE. Once we got to layer 5, now we have extracted the data that says that, oh, we've got, the GRE in this packet. And now we are ready. We store this information into a header FIFO and we store the packet into the data FIFO. And then we have multiple state machines. Now we're going to go through the one by one. The aligner state machine, which will read all this together, align them. The slicer state machine, which will take all this aligned data and then chop off the parts of the packet that you don't need and stick into another FIFO. And then finally, this final stage protocol replacement state machine that'll just take it out and replace the protocol value in the Ethernet header so that the final packet's ready to go. So that's about it. That's 10,000 feet overview of what we are going to be talking about. So now let's look at the very first section, which is the stage one. In the stage one, like in the diagram before, we have two FIFOs, and these are single clock FIFOs, two single clock FIFOs that will store the header and the data. And why do we need this alignment? Because when we did our parsing, let's say this was the packet. You had Ethernet header, IPv4 header, could be IPv6 as well, but IPv4 header just for sake of argument, and then GRE, and then IPv4 or 6 inside. Now this part is called the tunnel, and GRE serves as the tunnel header. What is inside in this case is layer 3 GRE, so it contains another IP header and then whatever layer 4 and so on and so forth. Just like a packet inside a packet. And what our goal is to remove all this tunnel so that it just becomes a packet. In fact, whatever was inside the tunnel becomes the outside. So that's what we're going to do. And now in the stage one, we are taking out this extra header that said, oh, we have GRE and here's the protocol value for the inside, blah, blah, blah. You basically get all this information that we did in our parsers. That information is stuck into this header FIFO whenever it was achieved, right? Somewhere deep in the packet, you found out that, oh yeah, this is it. But you need to line this up right here so that when we start chopping this packet up, we know exactly that this is the packet that we want to chop. Otherwise, we start chopping some random stuff and we end up with problems. So this is the first stage, is the alignment, and you can see these in myhdl allows beautiful modeling of whatever you're doing, whether it's a single clock or asynchronous FIFOs. You can do all of that. It's all beautiful, and it just emulates exactly like Verilog or VHDL. So that's great. Now moving forward, what is stage two? Stage two is going to be the actual slicing state machine, which will slice up the tunnel and then join everything back together so that the inside packet comes out, right? And then it'll stick it into this FIFO and on it goes. So let's look at the slicer state machine. What it's going to do. Now, packet look like this: Ethernet, IPv4, GRE, and then some inside IP, whether it's IPv4 or 6, and go on and on and on. That's the inside packet, like we said before. And what you really want is this Ethernet and that IPv4 or 6 joined together. And this we don't want. We don't want all this section to be taken out. And so once the first stage has aligned everything and we've got this, header aligned with the Ethernet, we are ready to do this slicing business. So we are ready to cut this off, and join. So perform all this surgery. We are ready. And the state machine of choice to do this surgery is going to be the stage two state machine. This state machine is going to take data and the packet as it comes in. It's in idle state. And from the idle, whenever it sees the layer 2 start, then it's ready to start chopping. It's chomping at the bits. Its scissors are ready. But you can't really chop till you get layer 3. So if you get layer 2 start a packet, but no layer 3, you go into this wait state. And as soon as you get layer 3, you start chopping again, because you have to chop between layer 3 and layer 5. So the chopping starts here. Now, if you so there's so many ways in which this can happen. That's the interesting part of the state machines, is they can handle all that. If you get layer 2 start and layer 3 start, you can come directly here. You don't have to wait for layer 3 to arrive. And then when the layer 5 arrives, layer 5 is where the chopping ends. So both these states are watching for layer 5. And whenever layer 5, the chopping stops, you start gluing things together. You start gluing the layer part of the packet into this packet. And then when you're done with gluing, which is where the layer 2 ends, you just go back to the last state and go back to idle. This seems like just like final ends of the processing. And then once that finishes, you go back to idle. So that is the state machine that will do all the chopping and gluing of the packets. Now, moving forward, let's look at a picture view of what this chopping and gluing really means at very high speeds, right? We're talking about hundreds of gigabits passing through our pipes. And these packets are going at very high speeds and they are parallel, which means that you get 256 bits of data in a single clock at 400 or 500 megahertz. Is flying by so fast. Each clock cycle is 256 bits, which what I call these as worm diagrams. And these worm diagrams will let you see how the hardware engineers are thinking about these little lines, squiggly lines, and these worm diagrams. So what happens is that, let's say this is clock 1, clock 2, clock 3, clock 4, clock 5, clock 6. This is a packet. This is a packet passing by on a very high speed. It passes by this GRE strip block. Now what's going to happen is that this is the starter packet, and then let's say in this clock cycle this is the layer 3, and then layer 3 continues on some point, layer 4 and layer 5 and all that happens here, right? So layer 4 happens here. Layer 4 is our GRE. So we come all the way up to layer 4. Layer 4 ends, and then this is the IP, and then continuation of the packet, right? So this is IP. What we want to do is chop off everything that is in the black here. These shaded black areas need to be off. And so what we need to do is take this, and glue this part back here so that we remove all that dark regions, and then we get the blue part here and blue part here, and then it becomes green. And now see that the way we are sliding all this into this, it may be that some of the green gets left over. So some of these worm diagrams help us understand that there's so many possibilities, right? It could be that this part lasts all the way to the end and there's just a little bit of a blue. And then if that happens, then how will this glue together, right? Because it could be that this start and this end all lie within a clock cycle, right? So because each clock cycle is 32 bytes. So it's a lot of data. and the end goal is to arrive here. So depending on what exactly was in the packet, your state machine is capable of handling all these corner cases, whether this start and this end happens in the same clock or over multiple clocks and different alignments. What you see here is that the magic lies in these two tags. The tag which tells you where in the cycle is this coming and where in the cycle is this coming. And then the state machine is very smart to align these M and N numbers and do the various kinds of choppings that are required and then gluing that is required to achieve this final product, right? So that is what the state machine does in this case. And like I said before, if you want to see this code, I'm happy to show it, but it's hundreds of lines of code, and I don't want to go over it in a short video to demonstrate how it really works. I thought it'd be nice to just show it in terms of these worm diagrams and make it so much more fun to watch. All right, so now that we have sliced it, once the packet is sliced and glued together, out comes this packet and gets stored into this data FIFO. Now, I need this FIFO because of the slicing, because there are pieces of clock cycles where the data is just not getting sent to this FIFO. And to have the continuous data, I need to basically pause so the data gets stored in a FIFO and then eventually gets pulled out in a one seamless start to end data together. So all the pausing business and cutting and all the making of the the final product all happens within this FIFO by this slicer state machine. So combination, these are the parts that the slicer machine and this data FIFO together hide all the complexity for this state machine. To it just looks like, oh, this inside packet just came out and it just comes out here. And when it's coming out, all you have to do at the end is replace the protocol value. What does that mean, replace the protocol value? Now, the Ethernet, which is in the beginning header, it contains a destination address, source address, and this type field. This type is what tells what is following, what is layer 3. And layer 3 could be IPv4, IPv6. It could be some other protocol as well, but most common are IPv4, IPv6. If it's IPv4, it needs to be 0800. If it's IPv6, it should be 86DD. Now, the thing is, keep in mind that this packet, the outside packet is IPv4, let's say, but the inside packet is IPv6. All sorts of possibilities are there. The outside is IPv6, the inside is IPv4, and so on. So we have to handle all that. So when we chop this packet up, we remove the outer headers, we take the inner headers out. We have to accordingly detect whether the inner header is IPv4 or 6, which previous parsing has done for us. And then we stick that into this type length field. And once we replace this, we are done. So that, in a sense, is this whole block, the GRE strip block that has these different FIFOs and 3 different state machines that do the job. And that's all about this video. So now that we have gone through the whole introduction to networking through this example project, you can now relate to how myhdl and tools like Wavedrom, tools like GTK Wave, all these work so seamlessly to help you design and test all the same ideas. In fact, in most cases, myhdl code can also be translated to Verilog or VHDL, and we can accordingly see that and convert them, and then eventually you can take those modules to your other tools, which are where you are synthesizing them or taking them to a real FPGA and so on. So all that is possible. This is just a starter. Keep in mind that tools like ChatGPT, Copilot, etc., are very capable of writing code in Python. MyHDL code is fairly proficient, and you might be able to give some good prompts and get good code out of ChatGPT, which you can quickly transform into the code that you can use in your simulation. So all that is added benefit of using the Python environment. I cannot say more good things about how Python has been easy to use compared to things like VHDL. Python is just so much easier. Everybody learns them fast and they can use Python so much quickly. So all that is great and helps you write code that much faster. and the machine learning is just an added benefit that will accelerate your development. So hopefully, if you've lasted this long, thanks for staying with me in this video series, and hopefully you enjoyed it. I really hope you enjoyed it because it really takes you from a beginner level all the way up to where you have been able to code all these state machines, these complex state machines in myhdl. At this point, you are not a beginner anymore. You are quite proficient with myhdl. If you have questions, contact me. Otherwise, hopefully you had a good journey, and I'll catch you another video with something else. Until then, take care and bye bye.